And so today we are blessed, in fact, we are lucky enough to have with us a distinguished professor in the person of Professor Vladimir Lobanov. I hope I got the name right. And then also we have Mami Magbini Tokpa, who is also a PhD student, and they are all with the Russian State Hydrometeorological University. And their presentation today will be focused on the statistical methods and the models for assessment of regional climate changes. And so that would be for the session today. It's already past the start time, so we'll kick it start. And then whilst you are here, please, if you couldn't register early enough, kindly visit the chat, and then you have the registration link. I'll repost it, and then you can key in your details so that we can have a record of you, and then we'll be able to send you, information about future seminars of the sort. And then also you can type in your name in the chat so that the organizers are able to keep record of everyone who is here. All right, so we'll start with Professor Vladimir's presentation. So, Professor.
Yes, good afternoon and good morning, ladies and gentlemen. Thank you very much for such possibility to present my research and the research my colleagues about here some asks from you about this problem. And may I start? Yes. The theme of my report, Statistical Methods and Models for Assessment of Regional Climate Change. And my main objective or aim to develop a general methodology for identification modern climate changes and estimation of the future projects or scenarios taking into account zonal and local features of climatic characteristics, and to realize this methodology on example of some regions. In this slide, you see different kind of regions when we worked. Kostroma region, small district in Russia, and the coldest region of the northern hemisphere, the Republic of Sakha, Yakutia, and the hot area of the northern hemisphere, the Arabian Peninsula, and the Central Africa, of course, the more interesting for you. And next slide. Okay, task of regional climate. When we develop this main direction of climatology, regional climatology, and main task of this climatology, first of them forming a formation of regional database, of course, of climate data for climate modeling and assessment of the quality, restoration of gaps or observation data, increasing of short-term time series to the long-term period, and the same period for comparison data results between each other. The second task, estimation of the form and of the statistical model. What kind of statistical model? Stationary, non-stationary, and estimation, obtaining of the parameters of these models for each station, weather station, meteorological station in the region. And the third one, generalization of the obtained indexes or parameters of stationary statistical time series models for the region, and identification of areas where the most significant modern climate change take place. Next task, selection of the most suitable physical mathematical climate model for the region based on the comparison of observation data on stations and the result of historical experiment of SMIP 5, SMIP 6 project models, and calculation of future climate projection or scenario according different kind of scenario, for example, ICP, SSP scenarios, taking into account the correction of the result of climate modeling on model errors, of course, and local features of the particular region. Next one. Next one. And what kind of methods we developed and what kind of models we developed. First of them, of course, statistical methods for estimation or homogeneity of empirical distribution and stationarity of the parameters of time series of climatic characteristics, because it is very important. This is assessment of quality, quality of data quality, because the result will be depend of the quality of our information. And second method for restoration gaps in observational data, in increasing the duration or size of time series on the basis of interrelationships with the longer time series in analogical sites in the same area. Yeah, and develop statistical models of time series, stationary sample or non-stationary models of linear trend and stepwise changes, and assessment of statistical significance of these models and parameters of these models. And the next step, kind of method, method of spatial or generalization of indicators or parameters of non-stationary models and identification of regions with non-stationary climatic characteristics. And we developed also statistical models of intra-annual fluctuation and spatial statistical model, and more complex statistical models for complex time series, which connect with a process of different time scales. Therefore, methods. This is our process superposition of homogeneous components of different time sets, and it is necessary to develop methods of decomposition, and obtaining quasi homogeneous process, choice of effective parameters, construction of the model of homogeneous component, and definition of interrelationships between them, and of course future climate scenarios and projections which necessary to correct, of course, using observed data, of course. That's the next slide, please. What result where we published our results in many publications, them textbooks. You see many textbooks for study process in our university, and some monographs for assessment of climate, current and future climate change in the particular regions. Please, next slide. And now I start about methods. A brief review about methods. First of them, assessment of data quality. What kind of methods we used or developed for this aim? Statistical methods for estimation of homogeneity of empirical distributions. What's problem? You see empirical distributions, and some maximum or minimum points will be out of non-homogeneous for this distribution. Therefore, it is necessary to estimate this. Is this really this maximum or extremes in this distribution or another distribution? Homogeneous this distribution or non-homogeneous this distribution? We use statistical methods for assessment of homogeneity, such as statistic of Dix, well-known Dixon test, and statistics of Smirnov graph. This is a formula. And main problem that this test were developed for normal symmetric distribution. And you know that empirical distributions in hydrometeorology are not symmetric. They have autocorrelation coefficient. Therefore, it was necessary to develop tables of critical value of this criteria to main properties of hydrometeorological information. You see the results such new assessment for correct assessment. One, statistical methods for estimation of stationary of time series. Stationary, you know, for assessment of stationarity, they used a well-known test, teacher test and student test. The same problem in terms of impact of this critical statistic, autocorrelation and non-symmetry. Non-symmetry. This we developed table of critical values for this situation. And you see as an example of assessment of precipitation in Northern Station, Dixon Islands, for example, change equipment of measurement of measure. You see the one kind of equipment, another kind of equipment, and this is you see that time series is not stationary, of course, and for assessment of climate change, we need to use the second part of this time series. Yes, and next group of methods for restoration of gaps in observational data, increasing the duration of time series on the basis of interrelationships with longer time series in analogous station. Real situation, we have observation and missing data or gaps data in the middle, for example, a short period of observation. You see, it is we can restore another firm information using data on the more longer time series, longer stations. Yes. This is particular our station, another station, analogies, and we use three main methods. Method of individual analogies based on the synchronic oscillation and using regression equipments with analogy for long-term period. The second method, spatial or space models. This is which connect fields of climatic characteristics in different years, or connect fields of the particular year and a historical for long-term period. And the second, the last method, models based on the seasonal function, because you see there is a seasonal function for different kind of meteorological characteristic, temperature, for example, radiation, solar radiation, and in some months we have gaps of observation. Therefore, it is necessary to restore this data using the kind of this function. This is a short one method, of course. Sorry. And this is an example of software for realization of restoration data. Yes, you see, program software. Yes, matrix correlation matrix, and this is a conditions for develop of the best equation and the result. You see, the result. And next step, time series model. There are a lot of kind of time series models, cyclic model, and so on. And at the first, we use the most simple model. Simple time model. What kind of simple time models we use? At the first, stationary model, but average not change over the time. Yes, and this standard deviation of errors from average value from mean. Practical standard deviation or natural variation. This is a natural variation, of course, because we don't know anything about changes. And two kind, another kind of models of non-stationary average, well-known model of linear trend. You see a time series and its approximation by linear trend. linear trend, and new model, such as a stepwise change, because we in one period with stationary average, stationary process, and after what from any this process changes this state and transfer to another level of stationary average, the same. This is a stepwise change. And we develop indicators or parameters of non-stationarity. Assessment of efficiency if difference between a stationary model and non-stationary models, any linear trend or stepwise change, more than 10%, more than errors of observation. And statistical significance, we used Statistica or Fisher Statistica, ratio of two variants, and stationary model variance and variance of the of errors of the particular linear trend or stepwise change. And problem how obtained year of stepwise changes. We use minimization of some of difference between two average, minimum. And for example, you see the particular time series, and you see changing in average from one level to another level. And in the down picture, you see this is a maximum of parameters delta, or minimum parameters of some of deviation, some deviation squared practical. We obtained this year, and this year on this graph of time series. Yes. And what about proving of this new model stepwise change? For example, you see. Proving of possibility use this stepwise change model. This model is suitable. You see some graphs, some pictures. Upper picture is a total annual runoff of all the rivers of Russian Federation. You see one level and change to another level. And annual temperature in Russia is one level and possible another level. And as alternative methods, linear trend process. But I see stable situation with average. And year seasonal temperature in Russia. This is another proof. We divide all territory of Russia into homogeneous regions, and obtain average time series of temperature in each region. And we use three kind of models: stationary model. This is a standard deviation, yes, of errors. Trend model and stepwise model. You see, then less standard deviation, then better this model. And this is delta difference between stationary model and a particular model of stationary average. You see, red color is the most difference. And Kostroma region is a particular the longest time series. The longest time series more than 100 year. You see, and this is annual temperature. This annual temperature depend on the temperature of the particular months, March, April, February, June. And you see the same change in monthly temperature. In March, stepwise rising. In April and February is the same. Yes, and what is the result of software? For example, we obtain delta and another parameters of non-stationary models, and as a result, this is species of non-stationary the region and identification of area where the most significant modern climate change take place. This is a red area, and you see during the year this area is changed, and not only location of this area change, and size of these areas change too. You see in March in the this is an area of Yakutia. Change of these areas of non-stationarity from north east to southern and after that in November in northeast too. And the second problem future climate. How to estimate future climate? Only we can.
My English is very good.
Thank you very much, but I don't sure. Don't sure. If you don't understand, please interrupt me because I don't have any practice during several years. Excuse me if you don't understand. What problems with the climate models, general circulation models? The first many models, you see increasing of number of models from SMIP 3 project to SMIP 5 and to SMIP 6 project, increasing for this model, and many models became as system models already. Uncertainty in scenario and projection. Uncertainty, a big uncertainty, especially to the future, of course. Different reliability of modeling different climatic characteristics. You see a correlation coefficient. You see enough high correlation coefficient for temperature, and less value of this coefficient for precipitation, for example. By what to do in this situation? What to do using all pool of these models, mathematical, physical mathematical models, or we can obtain the best model for best technology or regional identification of future climate assessment, regional assessment. The first step, selection of the most efficient climate model when comparing historical experiment data and observation for a joint period. The second step, estimation of systematic errors of the model over the region. The third step, correction of future norms or versus or according gradient, we move from when we move from observation to scenarios of projection, and as scenarios norms increase to the future to 2100 and the first step, space generalization. And you note that there are a lot of models. Of them you see, you see here in internet, for example. The first step, selection of the most efficient climate model when comparison historical experimental data and observation for joint period. This is particular region problem about assessment of thickness of this area using the winter temperature. And the result you see in table, result in table. We use several models, several climate models, and several station. This is triangular here, triangular. Station marked as triangular station, and this is a average difference. Mean and modeling using historical experiment data for this period mean for this period with the station, and you see enough big difference between for the average and we use any year temperature. We have not any correlation. We have not any correlation at all. For average, you see a systematical error. But second step, this is not a finish, because the next problem, a special distribution of this systematic model errors. We see that if we also we have average error in 5 degrees, for example, 5.3 or 4.9. Not big these errors, but special distribution shows us maximum errors or maximum difference can be to 10 degrees in eastern part of this region. Why? Because a descent here, this is a winter, and descent more cold in desert here. The third step, correction of model result. We use a condition of homogeneity of trends or present and future, and we see the same velocity of this trend in present, possible such velocity or rates of this trend will be in future too, because therefore we obtained average value for climatic models for 30 years period, and the 30 temperature growth rates or gradients we calculate using the following formula. This is for observed period, 2 points in observed periods, and 3 points in the future period. And correction, this is a formula for correction of scenario temperature, the future period, and for the observed period. You see, this one historical experiment, these ones is data information of historical experiment, two averages for 2 period of time, and 3 averages for 3 different period of time in future scenario, and it is necessary to correct because real situation lower. This is real situation of observed data in present. Therefore, and future situation have to be the same. We can increase scenario data. And the second graph about using 2 different projects, SMIP5 and SMIP6. Okay. And the third step, special generalization. You see special distribution of sums of negative air temperature, or no, for winter period, of course. This is negative air temperature is the main factors of maximum ice thickness. You see, and the result. This is the result. Space generalization or special distribution of some negative temperature in nowadays in the end in the end of our century. You see that a picture is different because this is a gradation of the winter, kind of winter. strong winter and soft winter. You see soft winter and situation with very mild, very warm winter will be better. And after that, transition to climate indexes. In our case, climate indexes is a maximum ice using equation or between sum of negative temperature and maximum ice thickness, we can obtain maximum ice thickness in the end of our century. And you see different gradation, of ice thickness. Blue, this is a very thin, not more than 10 centimeters, and gray between 10 and 20 centimeters, and more than 20 centimeters is white. And you see that area with white color is very small in the end of our century. And my conclusion, that is a stepwise model, which we suggest in many cases is more effective than well-known trend model. And stepwise temperature changes in the regions are most likely associated with a change of atmospheric circulation. There are seasonal and special changes in areas of non-stationarity. Seasonal space changes because not the same area of with big climate change. This area can change during a year, for example, more in spring and less in summer, for example. It is necessary monitor and analyze this area. And for each region, it is necessary to choose the more effective or appropriate climate models should be selected, and future climate scenario data, it is necessary corrected. Yes, thank you for your attention. I finished. I hope that you catch something from my report. Please, questions now or after my postgraduate student possible.
Sure. Thank you very much, Professor Vladimir Lobanov. So whilst I believe it's been a very interesting presentation. It's been very good, very detailed enough. And so Mami will be the next to present, but before Mami comes in, we'll allow for 2 questions. And then when Mami is done, we'll then take a bulk of questions again. So if there are any questions, you can kindly unmute, ask Professor Lobanov. So we're taking just 2 questions while Mami sets up his presentation slide and then get ready. Okay. But I don't see any hand from here, and then I don't see any questions in the chat yet. So I believe maybe our participants are waiting till the end, Professor Lobanov. So we'll take Mami's presentation, and then when we are done, we take a host of questions all together. All right. Thank you very much. And then Mami, over to you.
Good morning again to you, especially for those who join us now. And it is a great pleasure for me to participate in this interesting seminar to present the result of my research. And so at the beginning, I would like to ask you to be more attentive because of the language, and so I have to apologize for the quality. So let us go. My presentation topic is on the application of statistical methods and models for the assessment of current climate change in the air temperature in Central Africa, the method that the professor has already explained. So the attempt is to first time estimate the contemporary air temperature change in Central Africa during the 20th century using 2 non-stationary models for average. These 2 models are linear trend models and stepwise change model. And for the 7th time, we are going to estimate the future air temperature under the CMIP 5 and CMIP 6 project scenarios until the end of the 21st century. So talking about Central Africa, we consider in this study the area between 24 degrees north and near 14 degrees north and 14 degrees south, and between 6 degrees and 34 degree east longitude, which are presented here in the map. So on the map, we can see here the distribution of the weather stations, data of which has been used to modulate the climate change of air temperatures. So we can see that these points with VMO codes. So on the upper side of the map, we can see two graphics here. The first graphic explains all the distribution, the probability of the distribution of these weather stations. And here on the downside, the left side, we can see it is clearly presented here, the distribution of these weather stations. The red color and the yellow here present us a location of the weather stations with a high level according to the middle level of the sea. And the green colors present the stations with a middle level, and the blue color here show us the stations with a low level, as I said, according to the middle level of the sea. And on the upper right side of the map, we can see a graphic showing us the distribution of data according to their duration in the time series. So when we analyze the graphic, we see that much of the time, our time series that we use have a longer of 71 years. So with which data, for the data, data had a different beginning, and that is said to the different longer. So and the different qualities. In order to have a good result, we had to restore the missing data in the time series, which results are here presented in the table. We had 65 weather stations. So we see in the table here that after the recovering, the number of our time series are here in the first column. And in the second column, we have the number of year, or the longer of year, the time series here. And we see that they have increased after restoration. They are ranged, the number of recovery data are ranged from 28 in October to 36 in January and February. And one more thing important is to look like the error between restoration. These errors are ranged from 0.2 to 0.3. And the correlation coefficients between the recovering data and the original data. We see here that this correlation coefficient is quite good. It is they are runs from 0.91 in August to 0.95 in February. And the last column here is also important because they show us the number of stations, the neighbor stations that which data was used to recover our missing data. On the next slide here, we have, because the question is to examine, to evaluate the climate change in air temperatures. So we had to know before how the climate, the temperature look like in Central Africa at this moment. So that's why we constructed the average value, the norm of the climate, and for the characteristic months for each season of the year. When we analyze these maps, we see that in January, it was observed the most lower values of temperatures, especially in the mountainous regions here, and the other side in Cameroon here, we have a Mount Cameroon, it is a name there, and the only increase of temperature, high value of temperature is here observed on that side of our storage region. And in April, summer period, we see that there are warming, the low temperature here have increased, especially in the north of the territory. And still in the mountainous region, we have low value of temperature. And in July, we observed the global decreasing of the temperature already on all the territory, especially in this band here, from the mountains of Cameroon throughout to the coastal area here on the soft and join the mountainous region here. And when we compare these two maps in January and July, we see that the center of the region in January is more warm than in July here. So in October here, we see again that the temperature has again increased, because all the area we see here, which are cold in July, have warm here in the period of October. So in general, we can conclude that throughout the year, winter and spring and summer here are colder in the mountainous regions, and the east, the sea coast, and spring and summer are warmer. And as we know how the temperature look like in our territory, we had to pass to the modeling of the data to know which change has occurred from the beginning of the 20th century. So as the data quality was not the same in all stations, all points of observation, we proceed today to divide them into two groups. The first group was concerning all those time series that had a longer and a very good reliable data, and the remaining was the series in which were missing data and wasn't longer. So for the much longer series, we did a modeling. We formed the modeling in order to evaluate the non-stationary models, because here we use two kind of models, like I said at the beginning. So in the table here, we have the result of this modeling. First here, delta trend, delta TP, is an indicator of the non-stationarity of the model, linear trend model. And delta CT represents the indicator of the non-stationarity of the model stepwise changes. And R is the correlation coefficient of the trend model. And TCT is the year of the step changing. At what time, at which year the average, the norm of the climate change. So like we see, when we analyze the result, we see that before 1960, all the indicators have a low value, because as we see in the presentation of the professor, the non-stationary models value begin from 10%. When the delta increase data are more than 10%. So this model is non-stationary. So we see before 1960, all the indicators here are less than 10%. So we can conclude that the period up to, from the beginning of the observation up to 1960, the beginning of the 21st century, up to 1960, period are considered like a stationary period. And after 1960, we see that all these values here are more than or equal to 10%. So let us talk about more important things. As we have two models, we have to select the suitable model for our study area. So that's why we have calculated the average of all those parameters here. And we see that for when we compare these averages, we see that the model of Y step change are the best for our study area. And for the remaining stations, we modelize all these remaining points, remaining data, in order to know their dynamics in the year. That's why this map here shows us the result of this modeling. And it is important to notice that the gradients like we see here on the legend, the two last gradients are the gradient of the new stationary areas. So when we examine all these maps here, we see that the most new stationary areas appear in July and August and to September. So in January, we have they occupied the small part of the region and they have increased fuelly in February, March, April. So the conclusion in the dynamic of these non-stationary areas is that the most non-stationary areas has occupied has occurred in July and September, which can be estimated for the two-thirds of the whole territory. So, and like we have seen here in the result of the modeling here, the stepwise changes model has been the best, suitable for our study area. So that's why we had to know how this step change occurred or how the step changes are distributed in our territory. That's why we take all the step change years and distribute them in the territory. And we obtained this map. This map is very interesting because we can see here that all the step changes are grouped by the region, by the zone. It gives us the idea to examine if these zones presented by these colors are really a climatic homogeneous regions. That's why we proceed, because if these zones, like for example here, for the first zone here, if it is the climatic homogeneous zones, the correlations coefficient between these data here must be good, must be around 0.9, around 0.8, 0.7. So if we come out of this region, this correlation coefficient must decrease. So that's the work we do here. And we see effectively that these regions have a same climatic characteristic. That we obtain these 4 zones here. And in each zones, like I said, we constructed their climatic norms. And we see that in the first regions here, that is located here, we see that the norm has changed from one level to another. And in the second and third regions, we see that there was 2 changes from the first level to the second, and from the second to the third. So as it was known that there was 4 regions changes, we had to know how the climate, how the temperature has changed, the climate norm has changed in each regions. That's why we calculated in each regions how the climate changed. And to do that, we had to make the difference between the first norm, the second level here, and the first level. We will obtain the in how many graduates the temperature has changed, and the result obtained is we distribute them here on the territory for each characteristic month of the season in the year. And when we examine these maps here, we see that in January, there was the most growth of temperature occurred here in the northeast part of the region. And in the center, which is represented in the center and the south part of the region, which is represented by this color here, there where occurred least growth of the temperature. And here in April, we see that the growth of temperature is almost the same, excepted for the north part of the region. And in July, we see that comparatively to January, we see again that most growth of temperature occur here in the northeast part and in the south part of the region. And again, in the central part of forest region here, and there was a less growth of temperature. And the same in October here, we see that the temperature has changed approximately. The most growth of temperature occurred here in the north part and the south part here. The center part, there was a least growth of temperature, but more than in July and in January. So to know if this growth of temperature is statistically or climatically significant, we had to compare them to the natural variability. The natural variability, in other hands, we call it in statistical, the root mean square deviation, the standard variability, but the natural variability. We compare this growth of temperature here to the natural variability, and we see that in January, the most growth of temperature occurred are not too much in over the almost the same in over the parts of the territory, except that this northeast part here, and it occurred 1.7 to 1.8 degree here. So, and in the central part going toward the soft part, we see that the growth of temperature is not, didn't exceed 0.5, 0.6. And in April, it is confirmed that the most growth of temperature occurred in April, reaching the value of 2.7 degree in the north here. And in July, the growth of temperature is again already like didn't exceed a greater value of temperature growth. It is ranged from 1.2 to 1.3 degrees. So in October, we see that the growth of temperature according to the natural variability is again quite great. So in conclusion, we have to say that in April and October, we observe the most growth of temperature in Central Africa. To conclude this first part of our story, we have to say that the climatic characteristic of Central African temperature are that winter, spring, and summer are colder in the highlands and the sea coast, and spring and summer are warmer in the north than the other part of the region. And all temperature changes occurred in the second half of the 20th century. 20th century, yes. In the territory of Central Africa, we have to remember that 4 regions of homogeneous in the dynamic of changes in the average value were identified. And in 2 of them, the step temperature rise occurred twice. The first one occurred in the late 1970 years, early 1980 years. And the second occurred in the late 1990 years and early in the 2000 years. And in the second regions, the change step average temperature occurred only once. The first, it occurred in the middle of 1990 years or in the early 2000 years. And we have to remember again that in all seasons, the northern mountainous and eastern regions of the territory had the largest temperature rise to 2.2 degrees, which is 1.7, 2.7 natural gravity. And finally, in the central part of the territory, where there are tropical forests, the temperature increase in almost all the seasons except spring is small and does not exceed 0.5 and 0.6, which is less than the natural variability. So to continue, we have in the second part of our presentation to show or to present us the result of the assessment of the future temperature for our study regions. To do that, we use the global climatic models, which number are more than 50. And these models are made according to the global climate of the world. So to use it, like the professor said, you have to select the most suitable model for our study regions. That's why we have selected 9 here. Why? Because these 9 models here have historical data and scenarios data. And for these 9 models here, we compare their data to our observational data for the whole period and for the short periods of 30 years. So in this table, we have the result of the differences between the average value of the historical data and observational data for each model here. Like we can see, these modular differences are ranged from 2 degrees here for this model to 5.5 degrees. And in average, they are ranged from 2.8 to 4.3 for the model, Russian's model here. So we didn't end here. We see that there was another possibility to evaluate the effective model. That's why we divided that period of the period of the series temperature into 3 periods. The first one is from 1950 to 1975. The second from 1961 to 1990. And the third one is from 1976 to 2005. And we added the whole period from 1950 to 2005. And when you see here, again, these models, IPSL and BCC, are the most effective model for our region. That's why we use them to estimate the climate of the feeder climate of the feeder temperature of Central Africa. So in order to do that, we use the two last phases of the CIMIP project, which are CIMIP 5 and CIMIP 6. So we compare the data, historical data in these two projects, and the results show us there. This comparison consisted to draw what we call in mathematics straight line equation. So these equations have their parameters here. B1 is the gradient, and B0, like you know, is the intercept. So, and R square is the correlation coefficient. Delta CP is the differences of the average of each series. And delta maximum is the differences between the maximum of maximum value in each data, and data minimum is the differences of minimum in each data. And when we examine these results, we see that in the model IPSL, these two projects are very good correlated. And in the BCC too, they are very good correlated, but there is a difference, there are more deviations in BCC models. And then we compare these project data to the observational data to see how they are correlated. And the results show us that they are not good correlated, because when we see here the correlation coefficients, we see that they are ranged from 0 to 0.1. That is statistically insignificant. So this that is the same for the CIMIP 6 projects. And after that, it was important for us to compare or to evaluate the correlation in the two projects for the scenarios. We have here three scenarios has been selected: the scenario 2.6, scenario 4.5, and scenario 5.8.5. So as we can see here in the result, the indicators R squared and B1 are not here presented because they have the same value like in the comparison of the historical experiment here. So when we look at these different values here, we see that for the model, BCC model, we see that the deviation values range from 3.5 to 3.8. Comparative to the IPSL model, we see here they are ranged from 1.4 to 1.7. And so generally we see that there are again more dispersions, more deviations in the BCC model according to comparatively to the IPSL model. And generally these two comparison historical models and scenarios gave us the same result. So, and we didn't know if we have to use, because the this first comparison gave us a result that CIMIP 6 model is not quite very good than CIMIP 5. So we had to use these two projects to estimate our feature temperatures. But we realized that for CIMIP 5, the data ends in 2005. And for the feature data, it begins in 2006. And our observational data ends in 2020, 2021. So we had a period of 15 and 16 years. So we use this period for CIMIP 5 to estimate the correction of the data, if it is necessary to correct or not. But we didn't do it for CIMIP 6 because of the period, the common period, because in CIMIP 6 data, historical data ends in 2014, and the future scenarios begins in 2015. So from 2015 to 2020, 2021, we just have 6 or 7 years, which is not good for climate examination, climate modeling. So in the table here, we result for 2.5 scenario, 4.5 scenario, and 8.5 scenario here. We see that, or let us notice that here, we write here, CIMIC 5 are the data that is directly from the scenario, that directly from the project. And CIMIC 5 Corp is the estimated, corrected data. So we compare them to see how they are, if it is necessary or not. And effectively, we see that before the correction, we see that their correlation runs from 0 to 0.2. And after the correction, we see that the correlation increase. We see here it is 0.94 or 0.99, which is very good. And when we compare the differences between their averages, we see that before we had 0.4 to 1.9, which is big. And after the correction, we see that these differences has decreased, and it is run from minus 0.2 to minus and plus 0.3. So it is the conclusion is that it is necessary to correct, and the correction gave us a good result. So, and for that, we did the correction. We estimate the future temperature for Central Africa from now to the end of the 21st century. The example of the October, the example is showing here for two scenarios. The middle scenario is 4.5 and 8.5 scenarios for the each individual individual point of observation here. And on the graphic, we see how we did correction. When we look at the January here, we have 3 rows. The first row is here, the blue one, which represents corrected data, and the 2 ones here, the second, the red one is the row of the CIMIC 5 data, and the green one is for CIMIC 6. And for 5 periods, the 2 periods of the current moment and 3 periods from the future moment. When we examine the graphics, we see that in January, the estimated temperature, future temperature by the project were overestimated for CIMIC 5 and underestimated for CIMIC 6, and they have to be corrected to be according to the formula that Professor had already explained. And in April, we see that both of these projects have underestimated the future temperatures, and so for the July, they have estimated in overestimated in CIMIC 5 and overestimated again for CIMIC 6, and these both temperatures have to be pushed down and to coincide to realities. So,
sorry, Mami. Sorry, Mami.
Okay.
Mami,
no,
sorry. I think we have about. So let's do some 4 minutes so that we can make room for some questions too. All right.
Okay.
Okay,
just
sure.
the map here. This map here.
All right.
For the first line, we see it is represented, a special representation of corrected temperatures here for the first moment from 1981 to 2010, and we see that the temperature will increase at the end of the 21st century, we see almost on all the territory, the temperature will be runs to 28, 27, 28. And for the scenario 8.5, we see that it is very, very bad for the country, the territory, because at the middle of the 21st century, we see the temperature in the Central Africa will be around 2.28 degrees of temperature. So the conclusion is here, because we don't have time. You will see the conclusion here. So I thank you for your attentions.
All right, thank you very much, Mami. It's been also quite insightful. So we would make room for some questions. So we have about 15 minutes for questions. If there are any questions, you can kindly show by hand and then ask. You'll mute and then ask, or you can type it in the chat. Maybe let me kickstart. So this one is to Professor Vladimir. So I think you concluded on the stepwise method being quite great and then also showing more promise. Now I wanted to find out if the stepwise approach is variable dependent. Can it be used for, let's say, every climate variable estimation, or is it variable dependent, or it's just based on the availability of the data, and then that works well? And then also to find out when you were dealing with the homogeneity testing, in order to sort of make the data homogeneous, how do you ensure that you do not also remove the climate variability signatures? Yes, those are my two questions. Yeah. So the questions are to Professor Vladimir.
Yes, can I answer about methods? Of course, this empirical statistical method depend on data, quality data, size of data, of course, size of time series. It depends, of course, depend on the errors of data, of course. Therefore, it is necessary to use several weather stations and compare results in different sites each other, of course. And I gave information that not only linear trend model is suitable for approximation of a long-term time series, not only trends and velocity of trends, slope of trends, and a stepwise model is possible to use too. You see the real results that you see one stationary average, and after some year you see another stationary area average. This is connect with trigger mechanics of climatic system, stable system, equivalence system. Yes, possible, because the reaction of system to the external factors differ, of course. Therefore, two different group of models, a trend and stepwise changes.
Yes. Sorry to chip in. Can you repeat the second question again? Because it seems we didn't.
What about homogeneity?
Yes. So the second question is on the homogeneity testing that you did. So in trying to do the homogenization, how do you ensure that you are also not removing the signature of the climate variabilities?
Yes, of course. At the first words, I said this. It is very important to assessment of quality of data and homogeneity extremes, maximum, minima, of course, because this minimum, maximum extremes connect with the weather condition, not climate condition, because climate is more long process, and particular point influence impact of average, impact on variance, of course. And you see non-stationary result using Fisher test or student test. This is necessary to estimate homogeneity of empirical distribution at first.
All right, thank you very much. Okay, so we have a question from Maureen. Yeah, Maureen, please go ahead.
All right, Prof. and then Mami, thank you very much for your presentation. So back to Prof, with your new model and then your approach you are using, mostly in Africa here, data sparsity is a challenge. So you said we need to get good amount of data to be able to do this. So in areas in reality where we do not have this data sets in abundance, what will you recommend should be done? Can we still go ahead and use this your approach to be able to test this over us? And then secondly, if we have to go use, let's say, satellite data to be able to fill in this missing gap in there, to some extent, the impact of some of this climate variability there will also slightly be reduced compared to what is actually observed. What will you also say in that regards?
Okay, so just give me a second for me to translate so that Professor can understand what the question entails.
Sure.
The second part of question and can explain, but for the first part possible, Mami better explain about special distribution of weather station because he worked with this information more than I am, and I understood that in Central Africa data is not in many cases, especially in some countries, is not correct. It is not correct, and short period of observation too. And we try to at the first use only a more long time series with information which we prove this information. Of course, long term without a change of homogeneity, without change of measurement kind of equipment. And the first use this such approach. The first use more reliability, more quality information for assessment of area, and after that add another information using restoration of time series, because I said about different methods of restoration using the nearest weather station and field of climatic characteristic, connect one field in 1 year to another year of historical period. We use different methods from what is small value of station to more big value number of station, and from different periods of observation, the longest period of observation to another station, increasing the period of observation. And I don't sure about satellite data because very short period of observation, and the same data reanalysis data, you know this, because any data connect observation, any data, any database of reanalysis, satellite data, another kind of errors. If we measure in the particular station with preceding 0.1 for temperature, for example, or another situation from satellite, what errors of temperature you can find from satellite data? Not sure for the as area situation. Of course, area situation. Compare one place to another place. Of course, I can use satellite data, but only for the last period of, for example, 10, 20 years, 30 years. And we need the longest time series, more than 70, 80 years for assessment of this changes, any changes.
Just if the answer is not that clear, maybe I can try to maybe throw more light on explain some of the things. So basically, concerning the first answer, the question that Maureen asked, you know, he understands that in Africa we don't have much data, or maybe the time we started taking measurements is not, it doesn't go that far. So therefore they have methods to restore the missing data. So for instance, if you want to get data for maybe 100 years and we have up to 50 years, there is a method that I can use to get that data that you need in order to continue your research. And when we talk about satellite data, as the professor mentioned, we started using this satellite data from maybe not for a very long period, let's say 10 years ago, 20 years ago.
Quality of this data.
So the quality of the data too is something that we cannot, it's difficult to actually say that they are actually maybe correct and other things. So there are some errors. So therefore, sometimes we don't normally use them. But if you want to use it, you can use it for maybe just a period of 10 years or 20 years ago. And that is it.
All right, thank you.
Oh, okay. I think there was a first part that Professor directed to Mami. I don't know if Mami would want to throw more light on it. So I think the first part, Professor was talking about you using the spatial, trying to do a spatial, you actually did a spatial assessment from your work, and you had, again, with data being a challenge in Central Africa and the most tropics of Africa, how you were able to go beyond that. I think Professor threw some light on it, but he directed that if you had some extra info to add, then you could also add on that.
About missing data?
Yes, I think that was, Maureen, that was the first question, I believe.
Concerning
Yes,
the missing
so
yes,
okay, so you using that over Africa, let's say some part of Africa, you are testing that. And from your map, we can see more of your stations are even more aligned to the northwestern part than the south or southeastern portions. What would you say have been some of the challenges as you are doing that? And could this approach you are using now be replicated? Can it be useful over areas that will maybe have station less than what you have? Because Professor said we need to get good data or distribution to be able to use this method or approach.
And then, Mami,
Yes.
I think, sorry, Mami, I think the focus here is on the spatial scarcity, okay, not necessarily the sparsity in terms of the temporal data, but then looking at the spatial domain where there isn't a dense distribution of observation. Yes.
Like I said, in Africa, we had a problem in collecting data. Some of our weather stations are not equipped and are not very good to working. So we have problem with collecting the data. So for my case, like you see, I can show the presentation. Probably. Wait. Yeah, okay. Are you seeing the map? Yes, here we see that the distribution of the weather stations are not uniform. When we look at the Democratic Republic of Congo, here is not enough stations. It is because much of the stations here don't have a good data. Even we recover the missing data, they had still not be good because we use the method of interpolation and extrapolation. We use the data next to the neighbor data. For example, if we had here this station, it don't have the data, we use the data here and those stations next to them to recover the missing data in this station here. So if the next stations which data are being using don't have a longer time series, so the recovery data will have the same quality, because we are not doing it by ourselves. We're using the mathematical equations for regression equation to restore these data. That's why we see here we choose only the good and longer reliable data. That's why I said here in this part, to examine temperature change, we divided our time series into two parts. The first part, we selected all the stations in which we had a more longer and more reliable data to evaluate how the temperature changes. Before, after that, we add the remaining station in which there was not a very good quality of data. So, in conclusion, the recovery, the reconstruction of a missing data depend to the station that is around to the station which the data have to be recovered.
All right. Okay. Thank you. Sure. All right. So if there are any questions, kindly show by hand and then please ask Professor Vladimir and then Mami your questions. Okay, Joshua, please go ahead. Let me still ask this one to Mami. So, Mami, you see in the final parts you were talking of some temperature changes, all right? And I noticed that in the lower latitudes, that's towards the Congo ends, you had lesser, you concluded on lesser temperature differences. I don't know if that's clearly the case. Yeah. So I'm asking because, Congo is actually noted for all these, felling of trees and then cutting down of trees for, charcoal production and the rest. Yeah, so these are more human related activities. And we expect that through these activities, rather, temperatures are expected to increase because of these anthropogenic activities. Yes, and so is there any extra reason maybe for the observation in yours? Because you indicated that the temperature changes are rather reducing. That's in the lower latitudes. So you had a different, so I remember from the map, you had the northern end showing a very red, like a darker red, that's the northwestern part. And then your southeastern part had a blue shade. Yes, and then you made mention of the northern part having temperature changes going up or becoming greater. And then the lower latitudes, as the southeastern ends, having lesser temperature changes. And I'm wondering if these have any extra special reasons.
So I think you didn't very well understand. All over the territory, there is growing increase of temperatures. Just the increase of temperatures have a different speed of increasing. That's why when we calculated the growth of temperature, we compare to the natural variability. So in each part of the region, we have a different natural variability. It is much on the north next to the Sahel. Then the central where there is the forest. So the difference of this growth of temperature is not the same. That's why we see the differences of the increase of temperatures.
Okay, I think it's clearer now. I think I now get it.
Yeah. Did you understand?
Sure. Yeah, I do. Because I mean, I now get it. So, all right. So it's a comparison to the natural variability.
Okay.
Okay, sure. All right. Please, any more question? Our time is already up. So if you have any question, you can ask. If not, we would then be ending the session here. Any questions? All right. So since there are no questions, we'd like to say a very big thank you to you, Professor Vladimir Lobanov, and then also Mami Magbini Tokpa for the quality time and then the quality of your presentation. It's great to have you, share your research findings and then your work with us. And we'd like to say a very big thank you. There's on behalf of KNUST and then Ghana Meteorological Agency and then all other participants hosted here today. We'd like to say a very big thank you. And we hope to invite you again to, give us more from your research and then your findings. And wish you all the best in your research too. All right. Thank you very much.
For you too. Thank you very much. I agree for future meeting too, or future collaboration. If you have interest in our methods or our approaches, please, we always agree to contact with you, of course. Thank you very much.
Sure.
Okay.
Thank you. Thank you too.
Hopefully it will give our professors some opportunities to practice their English language.
Yeah. Sure.
Thank you
I'll be
very
very glad to
Sure.
pass.
Thank you. Thank you. All right. So to everyone, that's the end of today's session. Next month we'll be having another session that will be the 15th series of the Meteorological Virtual Seminar Series. And so we'll send the information ahead of time. And please, once you get the information, do well to register and then join us. It's open-ended. We just need to know, the participants who are joining in, and then it helps our speakers get to know the wide range of spectrum for which we are coming, and then they can tailor their presentations to meet our various needs. So kindly do all when next we invite you to please register and then do join us. Have a wonderful day and then all the best. Bye-bye.
Yeah. Thank you very much.
Thank you.
Oh.
Yeah. All right. Okay. Thank you very much and see you next month. And then Mami, thank you too. And thanks to Professor.
Okay. Thank you.
Sure.
Bye-bye.
All right. Bye.